Welcome back. I am absolutely pumped for today's explainer, because we're heading out on a quest to understand some of the highest energy, most mind-bending stuff in the entire cosmos. We look up at the night sky and it just looks like this quiet, twinkling tapestry of stars. But actually, that is just a tiny fraction of the whole story. The universe is literally buzzing with extreme invisible power. We're talking crushed stellar remnants and massive explosive bursts of radiation. So today, we're going to look past the limits of our own eyes and explore how we've actually managed to illuminate the invisible.
Okay, let's dive into this. Right off the bat, we have to grapple with this central mystery. How exactly do you see the invisible? We're talking about cosmic objects that don't emit a single photon of visible light, or phenomena with energies so intensely high that traditional telescopes just can't process them. They're completely dark to human eyes. So how do we even know they're out there? How do we measure them? Well, to answer that, we first need to confront the most famous invisible objects in the universe.
That brings us to Section 1, Monsters in the Dark, and the truth about black holes.
There's a ton of misunderstanding out there about what black holes actually are, mostly thanks to sci-fi movies, right? So let's bust a few of those pop culture myths. The whole idea that black holes are like cosmic vacuum cleaners sucking up everything in the universe, or that they're wormhole portals to other dimensions. Yeah, those are myths. In reality, they're massive, huge, concentrations of matter packed into unimaginably tiny spaces, creating intense gravity. To put it in perspective, if you took our sun and magically replaced it with a black hole of the exact same mass, the solar system wouldn't suddenly get sucked in. No way. The planets would actually stay right in their current orbits. The gravitational pull from a distance is exactly the same as any other object with that mass. It would just, get a whole lot colder. Now, things do get pretty weird when you get up close, specifically at a boundary called the event horizon. And it's really crucial to understand that the event horizon isn't some physical surface. It's not like the crust of the Earth or the plasma of the sun. It's actually a strict mathematical boundary. It is literally the point of no return, where the gravity of all that densely packed matter becomes so strong that absolutely nothing, not even light, can escape its grasp. As for what the matter actually looks like inside that boundary, well, that remains one of the universe's greatest mysteries. Moving on to Section 2, Spotting the Invisible, or How We Act as Cosmic Detectives. To spot these invisible giants, scientists have to look at how they affect their surrounding environment. And if you happen to be the matter that gets a little too close to one of these monsters, well, scientists have a highly technical term for what happens to you. Ready for it? Spaghettification. Yep, that is a real, actual scientific term. Because the gravitational pull is just so intense, if an object, like a star, gets too close, it gets squeezed horizontally and stretched vertically. It's literally drawn out like a long piece of spaghetti. It perfectly highlights just how violent and extreme the physics become when you cross paths with that kind of intense gravity. Now, what's really interesting about this next slide is this number, 1,500. That's the distance, in light years, to the closest known black hole to Earth, an object named Gaia BH1. Now, 1,500 light years might sound pretty far away, but on a cosmic scale, that's practically our next-door neighbor. It's a great reminder that these objects aren't just theoretical math problems. They actually exist right in our own galactic backyard. But let's contrast that neighbor with this staggering number, 13 billion. This is the distance, again in light years, to the absolute most distant black hole we have ever detected. It sits right at the center of a galaxy known as QSO J0313-1806. And since it takes time for light to travel across space, seeing an object 13 billion light-years away means we are actually looking back in time, seeing a black hole that existed very shortly after the universe itself began. Pretty wild, right? And if you want to talk about truly overwhelming scale, just look at this, 66 billion. Now, this isn't a distance. This is the mass of the biggest observed black hole we know of, TON 618. That is 66 billion times the mass of our own sun, all packed into a single invisible point. The sheer scale of these extreme objects is just so massive that it demands entirely new tools if we want to even begin to understand them. Which brings us to Section 3, the Fermi Space Telescope, our true instrument of discovery. To actually see the high-energy universe, we rely on NASA's Fermi Gamma Ray Space Telescope. It launched back in 2008 and was named after the high-energy physics pioneer, Enrico Fermi. And this brilliantly illustrates exactly why Fermi is such a game changer. Think about the visible light our eyes can detect, like the light illuminating your room right now. That has an energy of about 2 to 3 electron volts. That's it, just 2 or 3. But look at what Fermi detects. Gamma rays range from 8,000 electron volts to over 300 billion electron volts. So Fermi is out there observing light with energies thousands to hundreds of billions of times greater that our puny human eyes can process. It maps out an entirely different, spectacularly violent sky. Because it can see these mind-bending energies, Fermi has delivered an absolute highlight reel of scientific discoveries. It's found over 300 gamma-ray pulsars, which are these incredibly crushed, super-magnetized stellar remnants. It also captured the very first light ever seen from merging neutron stars, which, by the way, was an event that also sent out gravitational waves. And it allowed scientists for the very first time ever to trace a high-energy particle called a neutrino all the way back to its source, a monster black hole-powered galaxy billions of light years away.
Let's move on to Section 4, the gamma-ray sky and the Fermi bubbles. When you take this incredible gamma-ray vision and turn it back toward our own home galaxy, things get really interesting. Fermi's data revealed this massive, completely unexpected structure glowing brightly in gamma rays. We call them the Fermi bubbles. These are two vast bubbles extending above and below the plane of our galaxy, spanning a breathtaking 50,000 light years. Scientists think this giant magenta glowing structure is actually the lingering footprint of an ancient, massive outburst from the supermassive black hole at the center of our Milky Way, Sagittarius A star. And the crazy part, we had absolutely no idea this massive structure was even there until Fermi looked at the sky in gamma rays.
All right, Section 5, extreme cosmic explosions and gamma-ray bursts.
Let's move to and see how this builds. You see, beyond black holes, the high-energy universe is defined by violent, transient events, and the most intense of these are gamma-ray bursts. Understanding these bursts really shows us just how incredibly dynamic the universe actually is. Here's how it generally works. Step 1. A massive star completely runs out of fuel, and its core collapses, creating a stellar mass black hole. Step 2. During this chaotic collapse, an unbelievably powerful, brief burst of radiation, the gamma-ray burst, is emitted straight out into space. Step 3. By combining data from Fermi with other space and ground-based observatories, scientists can actually capture and trace these fleeting events. This exact sequence was used to study a really remarkable event known as GRB 200826A. Take a look at this quote regarding GRB 2008-26A. It says, "It's the shortest burst known to be powered by a collapsing star, and almost didn't happen at all. By analyzing the data, astronomers realized the specific gamma-ray burst was extraordinarily brief. The collapsing star barely managed to push its powerful jet of radiation out before the whole system just collapsed in on itself." I love this because it beautifully brings to life the chaotic, violent, and precise reality of high-energy physics. Literally, if that star's conditions were just slightly different, that burst would never have escaped, and we wouldn't have seen a thing.
So, the crucial point is this. The universe is not just that quiet, visible light we see from our backyards. It is a roaring, high-energy engine of collapsing stars, spaghettifying gravity, and massive invisible bubbles. And with tools like the Fermi Space Telescope constantly scanning the entire sky every 3 hours, we have to ask ourselves, what other invisible forces, massive structures, or extreme explosions are just waiting out there in the dark, ready to be illuminated? Thank you so much for exploring the invisible universe with me today in this explainer. Keep looking up, and I'll catch you next time.